Hello everyone, welcome to the course on hydrocarbons. In the previous lectures, we have studied alkanes, alkenes and alkynes. Now we will move to the next concept in the hydrocarbons, that is aromatic hydrocarbons. So these hydrocarbons are also known as arenes, since most of them possess pleasant odor. These are said to be arenes because they have the pleasant odor, and in Greek word aroma means pleasant smelling. From Greek word this term aromatic has been derived, and the class of compounds was named as aromatic compounds. And these aromatic compounds can be classified into two types. Those are benzenoids and non-benzenoids. Benzenoids means the aromatic compounds containing benzene ring. So benzene ring, as you already know, its formula is C6H6, and if the aromatic compound consists of this kind of ring, that is benzene ring, then such kind of aromatic compounds are said to be benzenoids. And non-benzenoids means the aromatic compounds not containing a benzene ring. Means benzene ring is absent. Other than benzene ring, the different rings are there, and such kind of aromatic compounds are said to be non-benzenoids. So these are the two types of aromatic compounds. Now let's see how we can name these aromatic compounds, that is nomenclature of aromatic compounds. Simply take one example. As you have already studied the IUPAC rules, the same rules should be applied here, but here we will take the benzene ring. Now simply if this benzene ring is there, then we will call it as benzene. Now suppose if there is a presence of substituent to this benzene ring, then we have to use the prefix, and here the substituent which is present is methyl. So then such a compound is said to be methyl benzene. Okay, so we have to use the prefix for substituents, therefore it is said to be methyl benzene. And simply if I consider the another example, okay, where it consists of nitro group, then it is said to be nitrobenzene. We have to use the prefix nitro because nitro group is there. So suppose if there is a presence of two substituents to the benzene ring, okay, so I will take one is CH3 and at another position NO2 group is there. Now how to name this? We have to number this chain first. So how we can number this? First see, methyl and nitro group are there. We have to see which one will comes first in alphabets. So methyl M and nitro N. So after M, N will comes. So we have to prefer the methyl first and then the nitro group second. So therefore the name of this compound becomes 1-methyl 2-nitrobenzene. 1-methyl 2-nitrobenzene. So this is the name of the compound. And again if I consider some more examples where the nitro groups are present at different positions to the benzene ring. Okay, so what is the name of this compound? Here nitro group is present at first position. Number this 1, 2, 3, 4, 5, 6. So in such case, what is the name of the compound? 1, 3, 5, how many nitro groups are there? 3 nitro groups. So therefore it is trinitrobenzene. Okay, so in this manner we have to name this. Instead of this, if they have given the compound in this manner, OH, NO2, NO2 and NO2. Now what we have to do? Here OH group is there, that is a functional group, and this ring, the benzene ring, and to that OH group is attached. This compound is said to be phenol. Okay, so you have to remember that it is phenol, and to this phenol 3 nitro groups are attached. Now we have to number from OH because it is a functional group. So 1, then you have to take 2, 3, 4, 5. So what is the name of the compound now? Sorry, 5, 6 it is. Okay. So now the name of the compound is 2, 4, 6. How many nitro groups are there? 3. So try nitro. Now we can't use phenol, benzene. Instead of that we have to use phenol. So 2, 4, 6 trinitrophenol. That you should know. And another thing, this position is said to be ortho position, and this position is said to be meta position, and this is para position. That you should remember. Again it is meta, okay, and again it is ortho. So ortho, meta, para positions in the benzene ring you should know. Suppose if they have given, write the structure of meta nitrobenzene, then what you have to write? At meta position, okay, you have to indicate nitro group. So that is meta nitrobenzene. And if they ask for ortho nitrobenzene, then we have to indicate nitro group here. So therefore, remember ortho, meta and para positions in the benzene ring. And this is how we will name the aromatic compounds. So next, what is the structure of benzene? The benzene was isolated by Michael Faraday in 1825. The molecular formula of benzene is C6H6. So initially, the structure of benzene was given by different scientists, but the accepted one is given by Auguste Kekulé. In 1865, he proposed the structure that you are observing here. So benzene having cyclic arrangement of 6 carbon atoms with alternate single and double bonds, and 1 hydrogen atom attached to each carbon atom. So if we write the benzene in this structure, you have to understand that here the carbon atoms are there, and to these carbon atoms H hydrogen atoms are attached. That you should remember always. Okay, so this is the structure which is given by Kekulé. And now resonance and stability of benzene. In benzene we will observe the resonance, that is delocalization of pi electrons will takes place. So first let's see what is the resonance and stability of benzene. All the 6 carbon atoms in benzene are sp2 hybridized. So here 6 carbon atoms are present and all these are sp2 hybridized. The 2 sp2 hybrid orbitals of each carbon atom overlap with sp2 hybrid orbitals of adjacent carbon atoms to form 6 C single bond C sigma bonds. As you can see here, the C and C, these 2 carbon atoms has formed the sigma bond, and that is formed by overlapping of sp2 hybrid orbitals. Okay, so here sp2 hybrid orbitals are overlapped and formed sigma bond, and again the remaining sp2 hybrid orbitals of each carbon atom overlap with s orbital of hydrogen. So now these remaining sp2 hybrid orbitals, they will overlap with s orbital of hydrogen atom to form CH sigma bonds. So each carbon atom is now left with one unhybridized p orbital. So now two orbitals are overlapped. One sp2 is overlapped with another C and another overlapped with H atom. And the remaining one unhybridized p orbital is represented in this structure. Now what happens to that p orbital? So now they will start to overlap with each other. The unhybridized p orbital of carbon atoms are close enough to form a pi bond by lateral overlap. Means they will undergo sideways overlapping to form a pi bond. So the pi bond is formed. And here the overlapping may takes place in between C1, C2, okay, or C3, C4 and C5, C6. In this manner also they will overlap. Or another possibility is the carbon atoms which consist of orbitals, they can overlap in this manner also. That is from C1, C6 and C4, C5 and C2, C3. So there are two possibilities through which they can overlap with each other. And thus we will represent two structures. Two different structures has been observed here due to lateral overlapping of pi bond or sideways overlapping of p orbitals to form pi bond. So aromaticity means whether the given compound is aromatic or not. That can be observed or known by aromaticity. So aromaticity, it indicates whether the given compound is aromatic or not. And here there are three conditions that should be satisfied by a given compound to behave as aromatic compound. Or if we find any aromatic compound, if we want to say it as aromatic, then it should satisfy these three rules. So what are those rules? One is planarity. They should be present in a same plane. All the atoms should be present in same plane. And second one is complete delocalization of pi electrons in the ring. So delocalization of pi electrons should take place. As in case of benzene we have observed, the pi electrons may shift here or may shift here or may shift here. So in this manner they will continuously delocalizing. And third one is presence of 4n plus 2 pi electrons in the ring where n is an integer. So if any compound satisfies this 4n plus 2 pi electrons in the ring, then it is said to be aromatic, and it is also said to be Huckel rule because it is given by the scientist Huckel. So how it works? 4n plus 2. So for a given compound, if we take benzene only, let's see, in place of n, I will add 0. 4 into 0 plus 2. So 4 into 0 is 0 and plus 2 is 2. So 2 pi electrons. Whether the presence of 2 pi electrons, is there any presence of 2 pi electrons? No. Now again add 1. 4 into 1 plus 2. So how many pi electrons now? 4 plus 2, 6 pi electrons. So now here you can observe the 3 pi bonds are there. If 3 pi bonds are present, then the number of electrons involved will be 6 pi electrons. Because each pi bond consists of 2 electrons. Any bond, not only pi bond, if we consider sigma bond, then that bond consists of 2 electrons and that is said to be sigma electrons. Now we are considering pi bond. So in that pi bond, the number of electrons will be 2. So since 3 pi bonds are there here, therefore the number of electrons in benzene will be 6, and that is satisfied by Huckel rule. So therefore it satisfies the Huckel rule, and hence benzene is considered as the aromatic compound. So in this manner we have to find whether the given compound satisfies the Huckel rule or not. You have to just follow the trial and error method here. So you can put 0, then 1, then 2, then 3. So if any one of that value gives the number of pi electrons present in that given compound, then it is considered as aromatic compound. So this is the aromaticity. Remember this. Then preparation of benzene. How we can prepare the benzene? One is cyclic polymerization of ethyne, that we have already learned. What happens here? 3 molecules of ethyne we have considered, and it is passed through red hot iron tube at 873 Kelvin. Upon passing, the pi electrons gets delocalized and forms bond with each other, and thus forming the benzene. This is one method to prepare the benzene. And another one is decarboxylation of aromatic acids. Decarboxylation, sodium salt of benzene, when it is treated with sodamide. Okay, sodamide means it is nothing but mixture of NaOH plus CaO, calcium oxide. Upon treating with this sodamide, this salt will gets converted into benzene along with Na2CO3. So it is said to be decarboxylation of aromatic acids. This is one method to prepare the benzene. Then another method is reduction of phenol. Phenol is reduced to benzene by passing its vapors over heated zinc dust. So when phenol vapors are passed through zinc dust, then it will form benzene, one of the important method to prepare the benzene. Remember this. Okay. So reduction of phenol in presence of zinc dust will give benzene. So these are some methods to prepare the benzene. Now let's study the properties, physical properties. Aromatic hydrocarbons are non-polar molecules and are usually colorless liquids or solids with a characteristic aroma. Almost all aromatic compounds have pleasant smell, and they are non-polar molecules and colorless liquids are present in solid form. And these aromatic hydrocarbons are immiscible with water. Since they are non-polar and water is a polar, so therefore they are immiscible, means they are not soluble with water but are readily miscible with organic solvents. Miscible means they get dissolved or they are soluble in organic solvents. They burn with sooty flame, means they will give the black color compound upon heating. So they will produce the flame which consists of black carbon particles. Okay, that is said to be sooty flame. And what are the chemical properties? Usually these aromatic compounds are characterized by electrophilic substitution reactions. Means these will undergo electrophilic substitution reactions. So how does these electrophilic substitution reactions takes place in benzene? That we will study now. So first one, nitration. A nitro group is introduced into benzene ring when benzene is heated with a mixture of concentrated nitric acid and concentrated sulfuric acid. So this mixture of concentrated nitric acid and concentrated sulfuric acid is said to be nitrating mixture. So remember this. What does nitrating mixture? Mixture of concentrated nitric acid. Nitric acid, it is indicated as HNO3, and concentrated sulfuric acid, it is H2SO4. So this mixture is said to be nitrating mixture. So when benzene is treated with nitrating mixture, then it will form a nitrobenzene. Here is the reaction. Benzene upon treating with nitration mixture then it will form nitrobenzene. This is nitro group, NO2, okay, along with water. Here nitro group is substituted to benzene to form nitrobenzene. So now how does this nitro group is substituted here? So let us study the mechanism of this electrophilic substitution reaction. And you should know the electrophilic substitution reaction mainly consists of, the mechanism mainly consists of 3 steps. First step is generation of electrophile. Generation of electrophile. So electrophile is generated first because it is an electrophilic substitution. Means we have to substitute the electrophile to the benzene ring. So electrophile, it is electron seeking. Means it usually has the plus charge on it. Then only it will attracted towards the electronegative compound or electron rich compound. So first step is generation of electrophile. And the second step is formation of carbocation. Formation of carbocation is the second step. And in third step, we will see the removal of proton. Removal of proton. So how does these 3 steps takes place? Here removal of proton means removal of H plus. So every electrophilic substitution reaction generally consists of these 3 steps. So in case of nitration, what happens? Let's see. First step, generation of electrophile. So here we have treated the benzene with nitrating mixture, that is H2SO4 and HNO3. Now I will write H2SO4 as HO2SOH. That is nothing but H2SO4 plus I have added HNO3, that I will write it as HONO2, that is HNO3, and this oxygen consists of lone pair of electrons, and this lone pair of electron abstract this hydrogen. So thus what it will form upon abstracting means it will attract the hydrogen atoms and forms the bond with it. Then what you will get? HONO2. Here the H will be present. And now the oxygen has valency of 2, but it has formed 3 bonds, and thus it will gain plus charge. And what will remain here after abstracting H? This bond will remain here, and those electrons will go to this oxygen atom, and thus forming what it will form? HSO4 minus. HSO4 minus will be formed. And now again what happens here? Since it has to maintain its valency, again these electrons will go to this oxygen and thus forming H2O. H2O will be formed. And here after losing the electrons, this NO2 will have lack of electrons now, because these electrons are moved to oxygen. Now what happens is this NO2 will get positive charge on it, because it has lost the electrons now. Now it requires the electrons, and thus it will gain positive charge, and this is said to be nitronium ion. And this nitronium ion, now it will act as an electrophile. It is an electrophile now. Now second step is formation of carbocation. In first step, generation of electrophile, for each reaction it is different. Step is same, generation of electrophile. It depends upon reaction, which substituents or which reagents you are using. Based on that, reaction will take place and generates the electrophile. And here the nitronium ion is formed. And second one is formation of carbocation. Now, the benzene ring, it is attacked by the nitronium ion, which is an electrophile. Okay. And this benzene is electron rich because it consists of pi electrons. So one of the electrons, they get attracted by this NO2 plus, here H is there. At all carbon positions, H is present. I will represent it one. And this H and NO2 bonds are formed. This H is already present, and now NO2 is formed by taking the pi electrons. So now when pi electrons are gained by NO2, this H or this carbon will get positive charge, which is said to be carbocation. And this carbon is sp3 hybridized. This carbon is sp3 hybridized because it has formed 4 bonds now. But it has lack of electrons, and thus this carbon is carbocation now. And this can be takes place at any position in the benzene, and it is resonance stabilized. That means we can write the structure like this also. Now here the H plus carbocation is there, okay, and here H, NO2 are there, and the pi bonds are present. Now in order to maintain the valency, these pi electrons will shift to here, and thus what we will get again here we will get the plus charge, because these pi electrons are moved here and here the bond is formed. Okay, and this will remain same, H, NO2, and here one double bond is there. Again, what happens here? This double bond will shift to here, and thus what we will get? We will get plus charge here and double bond here. Okay, and this H, NO2 will remain as it is. So this is how the delocalization of pi electrons takes place and forms the different resonance structure. The plus charge is formed here, here, as well as here. So this is how they get resonance stabilized. By forming the resonance structure, they will get stabilized. Means carbocation gets stabilized. And in general, we can write it as, or we can show this one as like this. Okay, that indicates, this dotted lines indicates due to the attack of electrophile, the delocalization of electrons will take place, or resonance will takes place. This is the hybrid structure. Okay, so formation of carbocation has been taken place. Now let us consider this one only. These are just resonance structures which explains about the stability, how they get stable. Now let us consider the carbocation now. Third step is removal of proton. Now in second step we have obtained the carbocation. Okay, so plus charge is there here, H, and double bonds are present. Now what happens? Removal of proton. Proton gets removed. Which one will gains that proton? HSO4 minus, that is formed here. It will abstract the proton, and thus what happens here? So when this HSO4 minus abstract this proton, this bond gets delocalized here, because this bond will remain as it is, so that will gets delocalized here. So when it delocalizes, what we will get? We will get double bond, here one double bond along with the addition of nitrogen, and here we will get H2SO4. So this is how we will see the electrophilic substitution reaction in case of aromatic compounds. So remember these three steps: generation, formation of carbocation and removal of proton. Next, second reaction is halogenation. Acids react with the halogens in presence of a Lewis acids like anhydrous FeCl3, FeBr3 or AlCl3 to yield haloarenes. Again, here is the reaction. Now, how does this takes place? First step is generation of electrophile. So, how does the electrophile is generated? So, once if you know the generation of electrophile, then you can write the formation of carbocation as well as removal of proton, because it is same in all reaction. Only difference is the electrophile which is present. This will also takes place as we have observed in case of nitration. Only thing is electrophile is different. So how does the electrophile is formed here? The chlorine gas, it will react with, here we have taken AlCl3. Now this AlCl3 is a Lewis acid that accept the pair of electrons. Therefore, by accepting the pair of electrons, it will form Cl plus, because this will accept the electrons and thus Cl plus is obtained and forming AlCl4 minus complex. So here Cl plus, now it is electron deficient. Now it requires electron. Thus we can say it is an electrophile and it is chloronium ion. Chloronium ion. Okay. Now it is an electrophile. Second step is what? Formation of carbocation. Formation of carbocation. How does this takes place? Again, benzene ring. Okay. And in that benzene ring, the Cl plus will attacks. So when it attacks, what it will form? The carbocation. Here the carbocation will be formed and here one H is already there and here Cl get attached and these double bonds are present. And a resonance stabilization is same. There in nitration we have written NO2, but in this case we have to write Cl. You have to write the resonance structures. Now I will not write the resonance structure, just I will simply explain the mechanism here. So this is second step, and third step is removal of proton. Removal of proton. And one thing remember, you have to write the resonance structures if they ask for mechanism. Okay. So simply in place of NO2 you have to write Cl. Okay. Now removal of proton. Removal of proton, what happens? Again take this compound in third step that consists of carbocation. What happens here now? Here AlCl4 minus, it will abstract this hydrogen atom. And when it abstract the hydrogen atom, what it will form? So it will form this bond, it will get shifted to here. Therefore it will form double bond here. And what will remain? Cl. Chlorobenzene will get remained. And here H is there and one Cl will react to form HCl. And AlCl3 will remain as it is. At the end we will get AlCl3 as it is along with the formation of chlorobenzene and HCl. This is how the substitution will takes place. Then third one is Friedel-Craft's alkylation reaction. Here also electrophilic substitution reaction takes place. What happens here? When benzene is treated with an alkyl halide in the presence of anhydrous aluminum chloride, alkyl benzene is formed. So here it is alkyl benzene. So now again same steps are involved here. What is the first step? Generation of electrophile. And this is one of the important reaction. It will be also continued in second year also. So therefore remember the Friedel-Craft's alkylation reaction. So first step is generation of electrophile. how does electrophile is generated? Which reagents we are using? Alkyl halide and anhydrous AlCl3. So what happens here? CS3Cl plus AlCl3. Now what happens? AlCl3 will accept the pair of electrons. What will form? CH3 plus will be formed, and here AlCl4 minus will be formed. So now what is the second step? Formation of carbocation. Formation of carbocation. How does this takes place? Now again consider the benzene. To this benzene, the CH3 plus, this electrophile gets attacked, and thus it will form a carbocation. So here what we will get? H is already there, and here CH3 get attached, and at this place the carbocation is formed, and it is again resonance stabilized. In case of nitration, here NO2 is present, but here it is CH3 now. Only difference is presence of electrophile. Remaining all structures are same. And then third step is what? Removal of proton. Removal of proton. So how does this takes place? Again consider the carbocation which is formed in the second step, H, CH3, H plus. Now it will react with AlCl4 minus. Now this will abstract the proton. So hydrogen has been removed, and this bond will shift to this position. Therefore, it will form AlCl3, okay, and HCl, because H and one Cl will react to form HCl, and along with what will remain now? This H is removed and this is stabilized. Now again we will get CH3, that is said to be toluene, or it is also said to be methyl benzene. So how you convert benzene to toluene? If they ask, then you have to write the Friedel-Craft's alkylation reaction. This is one of the important reaction, so remember this, and remember mechanism also for all these compounds. Only one general mechanism is there, so remember, for all the things you have to follow the same steps. Only difference is generation of electrophile, that you have to remember. Then next reaction is Friedel-Craft's acylation reaction. The reaction of benzene with an acyl halide or acid anhydride in presence of Lewis acids yields acyl benzene. So here acyl halide is present. So in Friedel-Craft alkylation, alkyl halide is there, and here acyl halide is there. COCl. Such type of compounds are said to be acyl halides. So now CH3COCl is there, it is said to be acetyl chloride. In place of CH3, there may be presence of C2H5, C3H6 or C3H7. Such type of compound may present, but this COCl will remain same. So how does this reaction takes place? Same first generation of electrophile. Okay. So how does the electrophile is generated? Here the reagents are CS3, C double bond O, Cl. This is acetyl chloride. It will react with AlCl3 again. So what this AlCl3 does? It will abstract the proton. So what will form? CS3, C double bond O plus. This is the electrophile now. Now second step is formation of carbocation. So in the formation of carbocation, what we will take? We will take the benzene ring, okay, and to that benzene ring, the electrophile gets attacked, that is CH3 C double bond O plus. Upon attack, what it will form? It will form the carbocation, okay, that is represented in this manner. So here it is C double bond O CH3, okay, and here the carbocation is formed. So third step is deprotonation or removal of proton. Removal of proton. So what happens now? We have to consider the carbocation which is formed in the second step. Okay, H C double bond O CH3. You have to write the resonance structures. Okay, that you have to remember. Here I am not writing resonance structure. They are same as in the case of nitration, and only electrophile you should change for every mechanism. And now here what happens? This one gets abstracted by AlCl4 minus. So hydrogen will get abstracted by this, and thus this bond will shift to here. So what you will obtain? The benzene ring along with C double bond O CH3 plus HCl plus AlCl3. So this is said to be acetophenol, that is indicated as COCH3. Benzene ring is attached with COCH3 is said to be acetophenol. This is the Friedel-Craft's acylation reaction. So in every reaction you have to remember which electrophile is generated. That electrophile you have to substitute to the benzene ring. That is only the product obtained during this electrophilic substitution reaction. So these are some reactions which are taking place in the aromatic compounds. So remember all these reactions. Now next, directive influence of a functional group in mono-substituted benzene. So whenever a functional group gets substituted, okay, or if there is a functional group is present on the benzene, so if any electrophile is coming, how it will direct that electrophile? Where does that electrophile gets attacked? Whether it will attach to the ortho or para or meta position. As you know, in benzene, okay, this position is said to be ortho, and then it is meta, and another one is para if a functional group is attached here. So first is, let's see ortho and para directing groups. So if any functional group is attached to the benzene, if that functional group direct the incoming group to ortho and para positions, then they are said to be ortho and para directing groups. So they will direct the incoming group to the ortho and para position. And examples are NH2, NHR, NHCOCH3, OCH3, CH3, etc. Okay, and these are said to be activating groups. Means these will activate the benzene ring. Let us consider one example, then you can easily understand that. I have taken the benzene. Okay, now this benzene is mono-substituted with OH group, that is alcoholic group, and this oxygen consists of lone pair of electrons. Now what happens? How it directs the incoming group? At what position it will direct? These lone pair of electrons will delocalizes here, and thus what happens? These pi electrons gets delocalized here. So what you will get? Here we will get the benzene ring. Here double bond is formed now. Okay, and here the bond is removed. Here double bonds are present, and since the electrons are shifted to this ortho position, here minus charge is formed. And again what happens? This minus charge will move here, and these pi electrons gets shifted to para position. So again what we will get? We will get this structure like this. here minus, here double bond, here double bond is 4 and here OH. So here double bond is formed now and here we will get minus charge. Again what happens, this will shift to here and this one will delocalizes to here. So what we will get now, the double bond, here double bond, now here minus charge, double bond OH. And now these electrons will shift here and these electrons will shift here. At the end we will get the double bond here, here and here along with OH with two lone pair of electrons. So again whatever the initial product is there, at the end the final product is also that is only. Only this shows that the delocalization of electrons. The pi bonds are shifted to different positions. So this is the resonance structure. And now from this what we can say, at which positions these will direct. If any electrophile E plus will comes to this benzene, where it will attack? It will attack either to the ortho position or para position. This is also ortho position. So since it requires the electrons, it will attack to the electron rich center or where the electron density is more. So in this benzene ring, at what position electron density is more? Wherever the minus charge is observed here, there the electron density is more. Therefore, this electrophile, it will attack either ortho or it will attack para position. So thus OH group will act as ortho and para directing groups. So remember this, and these are said to be activating groups, and these are some examples. And now some of the groups are direct the incoming group to meta positions and are called meta directing groups, and examples are given here: NO2, CN, CHO, COR, etc. And these are also known as deactivating groups. So now how does this can be explained? Let's see. Here I will take the nitro group, okay, and in nitro group NO2, one double bond is there, one coordinate bond will be present. And here what happens now? The oxygen will attract the lone pair of electrons, the bond pair of electrons to it, towards it. So thus what happens, when these electrons move here, these electrons will get shifted here. So again delocalization will take place. Now N single bond O minus, okay, the double bond, sorry, coordinate bond is formed, and here we will get plus charge, and remaining two bonds will remain as it is. Because here we have written plus charge because electrons has been attracted towards this nitro group. Thus now it is electron deficient, so it will get plus charge. Again what happens now? These pi electrons will shifted here to balance it. So therefore again what we will get? Here we will get the plus charge, and here double bond is formed and it is as it is. Okay. So here single bond and O minus. Now what happens? To maintain the tetravalency, these pi bonds or pi electrons shift here, and thus what happens? We will get the compound like this: double bond, and here the plus charge is formed at ortho position, and N O minus is formed. Again now what happens here? To maintain the valency, tetravalency, these electrons will shift here, this will shift here. Again we will obtain, so here we have obtained the double bond, okay, so therefore this double bond is formed here, and now the double bond, okay, so here we will get the double bond O and O along with these double bonds. So simply the delocalization has been taken place. So due to that delocalization, here in all the cases the double bond is present. So I have not mentioned here. So just write the double bond. So in this manner the delocalization will take place. Now you can observe, if any electrophile comes to attack to benzene, where it does attack? Will it attack to the ortho or para position? No, because these already electron deficient. Now if it wants to attack, then it has to attack to the meta position, that is somewhat electron rich or where the electron density is more. But this is rarely takes place. Okay, so it is very rare. If the meta directing groups are there, then only the electrophile will attack to the meta position, forming meta nitrobenzene. Okay, so these are said to be deactivating groups or meta directing groups. So remember all these things. So very important for CET. While solving the CET NEET JEE questions, this is very important. These electrophilic substitution reaction mechanism and ortho and para as well as meta directing groups. Based upon functional groups which are attached to the benzene, we can find the product, whether it will form meta or ortho or para product. Okay, so you have to remember these groups, okay, as well as the activating groups also you have to remember. And next is carcinogenicity and toxicity. So benzene and polynuclear hydrocarbons containing more than 2 benzene rings fused together are toxic and said to possess cancer producing property. So when in a given hydrocarbon more number of benzenes, okay, more than 2 benzene rings are present, then it is said to be toxic and produce cancer, and that property is said to be carcinogenic or carcinogenicity. Okay, so these are some examples that I have mentioned here. 1,2-benzanthracene, 3-methyl-chloranthrene, 1,2,5,6-dibenzanthracene, and 1,2-benzpyrene. So these are some examples for carcinogenic compounds. Okay, and this is all about hydrocarbons. So remember all these concepts. These are very helpful for CET, NEET and JEE.